Good afternoon or good morning. I'm Ray Wolf at the National Weather Service office in Davenport, Iowa, and I'm pleased to present Dr. Walker Ashley from Northern Illinois University. Walker is both an atmospheric science and a physical geographer, and that combination is a really powerful combination that makes for the opportunity to look at hazards, weather and climate hazards, both in the past and in the future. And we'll take advantage of that in his presentation today. But he and his students have done some wonderful work over the years. There's a link in the chat to Walker's webpage that has a lot of that research that is very applicable to what we're doing in weather service with impact-based decision support services. And in addition to his academic side, Walker is also a storm chaser and photographer, and has got some really neat stuff, as you can see from the introduction, the slide introduction here. So without further ado, if you have questions along the way, we encourage you to put those in chat and we'll address them at the end of the presentation. So off to you, Walker, and thanks for joining us today.
Well, thank you, Ray, and for the invitation to speak with you all today, and Jenna, of course, for setting this all up behind the scenes. As Ray and Jenna have mentioned in the chat or via audio, you can reach my research at my homepage there, chubasco.niu.edu. I tend to, even if the publishers don't like it, I tend to put PDF copies of my research out there and just wait for the takedown notice. So it's generally freely available for you to grab some of my research. So yeah, as Ray mentioned, we're going to talk about thunderstorms, their kind of historical perspective, but most importantly, considering the rapid changes that we're seeing both environmentally and in society, we're going to look towards the future as well. So I want to discuss, ultimately kind of the changing hazard landscape that seems to be gripping the world. I mean, I don't think you need to go to a news site today. I think we all know that there's going to be a front page story on the heat waves gripping not only the United States, but certainly Europe. So from fires to floods to severe storms, the frequency and the magnitude of these events seems to be changing. It's really a multifaceted issue, which I hope to discuss by at least singling out one specific hazard producer, and that is severe convective storms. So after every tornado, or it seems like severe weather disaster, we are often asked by media, I know in my institution, our respective PR folks, the public, or even our friends, colleagues, and I know in my own household, my children, is climate change to blame for that specific event? And I'd like to examine this question today using severe convective storms as a marker for assessing fundamental questions such as, is the world becoming a more dangerous place? Of course, we put on the news today, it seems like it certainly is. If so, is this due to climate change or other factors? And what can we expect in the future with these specific events? And ultimately, the really tough stuff is, how do we prevent this moving forward? We know that disasters are part of history, but they seem to be becoming more commonplace and particularly more impactful. How do we prevent these moving forward in the 21st century? So let's set the stage with sort of a global perspective on our society. As the late Dr. Sagan said, this pale blue dot, we often forget about how small we are in the grand scheme of the universe. The 20th century was really unique. Population growth, this is the last century, of course, unprecedented and breathtaking rate of growth, doubling twice. And this placed increasing number of people in hazardous settings and left many wondering what the carrying capacity of our planet is. With a current global population of about 7.8 billion, projections have us hitting close to 10.5 to 11 billion by 2100. And as you can see here, most of the 21st century growth is concentrated in Asia and the very socially vulnerable Africa. Now, variations on this growth estimate are expected, as only a slight change in the average number of children per mother can be a difference in billions of people. A consequence of the improvements in health and technology has been an aging society, which is illustrated by the swelling of the population pyramid projected to 2100, as you see here. Beyond being a really socially vulnerable demographic, and an aging populace is going to place a huge burden on our healthcare systems as well as funding structures. Of course, economic growth has been a recent advancement in our history, with GDP growth most notable in the so-called Western world, though many regions have seen economic growth, at least as measured by this one would call relatively cold and crude estimate. A better, more inclusive measure may be something like the Human Development Index. And this index actually includes dimensions of life length, overall health, knowledge attainment, and standard of living. But I'm going to have to leave that discussion for another day and debate. Of course, economic growth has meant a change in income across the globe, evolving from a relatively poor society where we had approximately 80% of the planet living in what we'd consider extreme poverty by today's standards, to a bimodal distribution that featured a so-called developed world that was 10 times richer than the developing world, and more recently, significant income growth in both South and East Asia at rates faster than those in even rich countries, or quote-unquote rich countries. And with the rising incomes, extreme poverty has fallen considerably. It's faster than ever before in human history. This is a remarkable achievement for society, but one I think we'd all agree we can't be happy with until it is eradicated. And with progress, we have inequality, and inequality growth does not happen equally as fast everywhere or between segments of society. We've seen the richest get richer, while the poorest have seen robust income growth as well. But there is a segment in the middle. Many of us are in that segment where the low to middle income class in the Western world has not seen the same income growth, which, we can debate about, but this might be partly to blame for our current politic that we're not only seeing in the United States, but other parts of the world. We can examine this inequality by looking at the so-called wealth pyramid, which illustrates in this case that roughly 1% of the global population holds nearly 40% of the global wealth. The top 10% has nearly 83% of the wealth. And a remarkable statistic from Oxfam, 26 people on this planet own the same as 3.8 billion people who make up the poorest half of humanity. Of course, as new markets have opened and economic growth, both domestic and international growth has taken hold, we pulled more and more resources and expended more and more energy. Much of this, and I don't think I have to convince you, but most of this, as you know, has been in the form of burning fossil fuels. And with this burning, we've seen a steady growth in CO2, methane, and so on, despite periodic international efforts to inform the global community on the need to curtail these greenhouse gas emissions. So we all know that climate is changing rapidly, at least compared to natural variations that have occurred throughout Earth's history. And we know that greenhouse gas emissions are causing mean temperatures to rise, as well as many secondary and tertiary effects. Some of them we don't completely understand. We know that the climate system, and most of you working within that climate system, is infinitely complex, and that we don't have a full understanding of the implications of the system's changes and how it may manifest. And of course, this occurs down at the local scale, such as a severe convective storm as well. But one of the potential benchmarks of a changing Earth atmospheric system may be kind of disasters, what we call quote unquote disasters. If there's one thing I can get you to take away from this talk today, is stop calling them natural disasters. They are anything but natural events. So when we look at disaster event data, we often see upward trends, such as this product, as you all know, from NOAA, which examines so-called billion-dollar weather events and climate events that have affected the U.S. Now, a trend line would reveal a significant upward frequency in these events, and the cost from the 330 events has been roughly $2.3 trillion adjusted for inflation. Of note, at least to me, is the increasing length of the green box, which is the topic of today's lecture, which is severe convective storms and their perils. So a natural reaction to a chart like that would be to think, well, is climate change to blame for this and other disaster changes that we've witnessed in the last few decades? And we as a scientific community are often asked about what's causing these trends, and a reporter invariably asks, is climate change to blame? Was this event caused by global warming? But many times the question itself is wrong. Can climate change be blamed for a tornado or a hurricane or a weather or climate hazard? When really we should be asking the question, is it a contributor to the change in frequency or magnitude of event? Now, singular event attribution is a really serious challenge and remains quite difficult. And attribution science itself is quite nice. There's some great samples of the attribution studies. I don't know if you're getting these, but in the BAM supplements on an annual basis, you see this explaining extreme events series, which is quite good. And these attribution studies are using a couple of different approaches to get at this. A lot of times they're using modeling, but sometimes we often try to standardize and remove the human effect to see if these are changing. Now, the simplest case is actually take an event such as a hurricane, simulate it under historical conditions, and then modify the environment so that the same event experiences a future warming scenario. We call that a pseudo-global warming approach. We look at the delta in those changes, and those of you that have tried this know that it is not as simple as I'm alluding to. Other studies have tried to actually normalize humans from disaster data, that is to examine the trends in a disaster after you have controlled for things like GDP, wealth, or population. Now, I really don't like that approach because this removes the human component from the system that we all really must study, which is the human dynamic. So before we get into the nuts and bolts of what we're going to talk about, which is a changing severe convective storm disaster landscape, let's turn our attention to the relatively short history of what we call disaster research, at least what us academics call disaster research. Now, in the early to mid 20th century, disasters were considered acts of God, and you've probably heard that term before. That is, that they were divine punishment for our moral misbehavior. Unfortunately, many of our policymakers, I don't think you have to go too far in the news to find this, but many of our policymakers, our attorneys certainly, and our insurers still use this as a defense for negligence. Then came along Gilbert White, and particularly in the 1950s and 1960s, and he led the way in the latter half of the 20th century, developing a school of thought, something called human ecology, which is about the relationships between people and their environment. Now, he argued at the time that disasters are not physical phenomena outside of society. They are linked to our decisions to settle and develop in hazard-prone land, often, of course, for economic motives. Meanwhile, many governments, and certainly our friends in engineering, continue with the thought we should contain extremes through engineering. Now, you know the New Deal and public works projects throughout the 20th century put a focus on steel and concrete as our defense against these events. Of course, in meteorology, we saw the advent and maturation of prediction and warnings, which have saved countless lives and is one of the world's greatest and certainly unsung, I think we'd all argue, technical achievements over the last century. Now, with Marxism and so on, sort of the radical academics in the 1960s and 1970s, social science research realized that disasters are caused by root social structures that cause extreme events to affect people differently, as well as determining their coping after an event occurs. So this gave rise to a broad understanding of what we call vulnerability science, which is illustrated at least succinctly, although it's quite complex here, but throwing it all on one slide, this is what we're doing here. This is the so-called pressure and release model by Wiseman et al. And it's boiled down to the root causes, which you can see over on the left, lead to dynamic pressures and unsafe conditions that when they combine with an extreme event, many of us understand the extreme events, when they combine with that extreme event, they create a disaster. And ultimately, a person's economic position, as well as any social and political linkages, determine how they are affected by a hazardous event. Now, I know that there's a lot on this slide, and goodness, it's a really important one to digest. And I just ask that if you're interested in how social vulnerability, socioeconomic vulnerability affects disasters and where they occur and their magnitude, that you do a little research on this pressure and release model because it is a fascinating area of research. So today, if you talk to a disaster researcher, we now focus on the interactions of both human and physical systems. We try not to look at each one in isolation, because we know that the disasters are a product of society and are caused by these extreme events interacting with socioeconomic vulnerabilities through really multifaceted human decision making. Now, again, just because disaster researchers focus on these interactions today doesn't mean that we see this in the real world or in practice, and certainly with our policymakers. So now let's turn our attention to severe storms. Of all the hazards, which you can see over here to the left, that we can examine, the severe convective storm is near the bottom of our understanding and confidence in attributing the event frequency or magnitude to climate change. Yet it is these events that many of us get phone calls for immediately after they occur, wanting this binary yes or no response to the question, is climate change to blame? So before we look at the future of severe storms, let's take a look at the historical climatology, at least from what we know right now. So using a US-centric approach, what does the climatological record tell us about at least the severe storm frequency in the contemporary record? For those that, of course, have worked with these data, you know it can be quite difficult to untangle meaningful trends, but with care, one can begin to discern if any patterns exist. And most of the research suggests that there are no significant changes, at least to date, in the tornado and hail frequency data. Though there are some interesting findings. For instance, my colleague here at Northern Illinois University, Victor Gensini, has revealed quite a substantial and significant change, an eastward shift in the environments that are supportive of tornadoes. Harold Brooks and others have noted an increased tendency for tornadoes to cluster on days, though this pattern remains unexplained. So let's look to the future of severe storms, and we're going to look at it from two different sort of methodologies, using what we call an implicit and an explicit method. So initially, research that has assessed the impact of climate change on SCSs, or severe convective storms, and their populations has employed the implicit approach. And another term for this is the environmental proxy approach. Now, this is illustrated on the left, and it uses relatively coarse resolution output from GCMs, or global climate models, to assess how the overlap of at least 3 of the 4 fundamental ingredients for severe convective storms, moisture, instability, and shear, may modify, adjust in days or other similar metrics in the future. Now, the second approach, as illustrated on the right here, uses what we call regional climate models, or RCMs, to explicitly simulate convection at very high resolution. In the case here, about 3.75 to 4 kilometers. Now, this provides really robust climate information at the regional and local scales. Here are some simulations that Victor Gensini has run, my colleague here at NIU. And the purple there is actually synthetic severe weather reports that we've generated with these simulations. Now, these simulations off to the right overcome many of the errors and uncertainties generated by parameterization schemes that we see within GCMs. But because of their high resolution and the fact that we're running these for years, they come with significant computational expense and, of course, storage problems as well. So typically, this explicit approach uses a dynamical downscaling technique where a relatively coarse GCM output is used to inform a regional climate model, such as the WRF, to provide more detailed insight into the future. So what do the 2 different camps of the research suggest, at least to this date? The implicit research, which I kind of summarize off to the left, this has been led by a lot of the people you see down at the bottom, today suggests that there will be increase in the number of days supportive of severe thunderstorms, and that's key. This is an increase in the number of days, at least supportive. Doesn't mean you're actually getting them. It just means that you're supportive of thunderstorms during the 21st century. Though there is a bit of complexity in that, specifically with individual severe thunderstorm ingredients, which I try to surmise down on the bottom left. Now, the explicit research, the simulation, high resolution simulations, led through this dynamical downscaling technique, at least those simulations produced to date, which is again hamstrung by the massive computing expense and data storage issues, suggest that severe convective storm events may become more frequent and their seasonality may become more expansive by the end of the 21st century. So I want to zero in on some of the simulations we've done over really the last 2.5, almost 3 years. It is taking a considerable amount of time to produce these simulations. We call this the WRF BCC, which is the WRF ARW that has been forced by NCAR's GCM called the CESM, which was for the CMIP-5 program. What that means is we're taking NCAR's GCM and forcing WRF in these sort of regional climate simulations scenarios to get decade-long simulations, and then we tease out populations of severe convective storms, maybe a mesoscale convective systems. We can even pull out things such as high rainfall rate events, or even climatologies of CAPE and SIN and so forth. What I'm going to show you today is some of the output from this CONUS scale. Again, we're at 3.75 kilometers with output at 15 minutes. And I'm going to show you the historical run. We'll compare the historical, which is 1990 through 2005 water year. Basically, water year starts October 1. And we'll look at the future. We're going to look at 2 different future scenarios. We'll look at the end of the century in a so-called pessimistic, this is the so-called worst case scenario. I hate to give it all this terminology, but it's the RCP 8.5, which is a very pessimistic warming scenario. And then we'll look at more of a balanced 4.5 or so-called intermediate warming scenario, which is more than likely more realistic at this point. But you know, there's lots and lots of debate about which scenario is most realistic at this point. I'm going to leave the mid-century. We just completed the mid-century, mid-21st century simulations out of the conversation today. Just because I haven't had really the chance to process those data. They're quite significant, and we just completed them in May. So I'm going to illustrate some of the output, that at least a couple of the areas of study that we've had to date. I got a lot of grad students working with us, our colleagues, Victor Gensini, Allison Michaelis, Alex Haberly. We're all working on different aspects of employing these data. And if you have any interest in working with these, I invite you to reach out to us, and we'd be happy to have more people. There is literally half a petabyte of data to go through here, so it's more than significant than just a single team of researchers to get through. So actually this paper was just formally published today, and this study led by Alex Haberly. We looked at just simple thunderstorm events and looked at simulated reflectivity. So we using DBZ, or simulated reflectivity, in the future versus historical, or just basically looking at the deltas, we want to know if we're going to see more thunderstorm, more severe thunderstorms, at least as a surrogate for DBZ in the future. So what I'm going to show you, just a couple of quick pieces from that study. And on the left we have on the column, on the left column, we have the 4.5 scenario minus the delta. And on the right, we have the 8.5 minus the historical, not delta, but they are deltas of the future versus the historical. And then at the top, we have 40 dBz, 50 dBz, and 60 dBz thresholds. So one could think of moderate, strong, and potentially maybe severe proxies for thunderstorms in this simulated output. So overall, what you can see is as we increase the dBz threshold, generally more and more of the central and eastern CONUS can expect an increase in frequency of strong storms, at least as measured by dBz. And this is also illustrated on the right with what we call a cumulative frequency diagram, which reveals significant increases, at least in this case, of the 60 dBz. We really do see this demarcation, and we don't see much change in the 40 dBz, but once we get up into the higher thresholds of 50 and 60, you see this separation. And I'm just showing you the 60 dBz theoretically by the end of the year. By the end of the century, we see a lot more high reflectivity days in the eastern particular part of the CONUS. Now, there are some regional differences and discrepancies here that I don't have the time to get into here, but I invite you to take a look at the paper if you want to get into the weeds a little bit. Now, me personally, I'm really fascinated by this particular type of storm structure, which is the supercell. And why? Because I think they're fascinating. They're beautiful structures, especially when they're naked like this over the Kansas plains. But secondly, they also, of course, produce most of the significant severe that we're interested in: significant tornadoes, significant hail, and significant damaging wind. So how might climate change affect their frequency, intensity, and spatio-temporal distributions? Now, ultimately, the storm attributes will be modified in the future as the environmental ingredients supportive of supercells, such as strong shear, robust storm relativisticity, CAPE, and some convective inhibition or SIN, but not too much of that, ultimately is going to be altered by the kinematics and thermodynamics in a warming world. Now, like operational forecasting or other climatological research that's recently come out, we use updraft helicity, or UH, from the simulation output as a surrogate for rotating thunderstorms. UH is defined as a vertical integral of the product of velocity and vertical vorticity between, in our case, we're looking at the 2 to 5 kilometer mid-levels of the storm. Now, this is frequently used in both deterministic and ensemble forecasting to kind of look for the presence of mesocyclones. If we just kind of sum up the UHs or the mesocyclones across the CONUS, this is the result that we get. Comparing the historical in green and the future 4.5 and the 8.5, which is again 8.5 being the pessimistic warming. Broadly, the take home is that the count ceiling is much greater for particularly intense mesocyclones in the future, with more frequent intense mesocyclones for seasons except for the fall. And at the end of the day, the strong correlation between updraft helicity and severe storm perils suggests that this would lead to more hazards in the future, especially when we talk about tornado and hail events. So my co-author, Alex Haberly, developed an automated tool to identify, track, and catalog UH, what we call swaths. You can think of a Nike swath. That's kind of what we're doing here. Effectively, a swath that meets or exceeds certain criteria represents the footprint for a supercell. Now, I don't want to get into the weeds, but effectively we call it a supercell any 2+ hour long updraft helicity track that exceeded 75 meters squared per second squared. And you can see these illustrated not only the zoomed in scale here, Oklahoma to the left, but also sort of a seasonal perspective over on the right as we look at the simulations, and the black being the tracks or the swaths of these supercells during a spring event simulated in 1993. So just a couple snapshots from this study, which is under review after a round of revisions in an AMS journal. And we're looking at the left here, there's a change in what we call supercell track counts per year across the CONUS, with the top panel is the 4.5 minus the historical, and the 8.5 on the bottom panel are the pessimistic warning scenario minus the historical. In both cases, you can see the trend is for less supercells in the plains, particularly central, northern, and high plains, and more supercells in the east, especially across the lower Arkansas, central, and lower Mississippi and Tennessee valleys. Now, this is actually quite like the observed trend already found in the significant tornado parameter and tornado reports by Victor Gensidi and Harold Brooks and others. And our RCM data suggests that the historical trend of more east, less west is likely to continue under future climates. Some more kind of broad statistics here, looking at cumulative frequency diagram illustrating the means in the 25th and the 75th percentile bounds of the epochs that we examined. Again, green historical, blue the future 4.5, and the red future 8.5. So while there is a rather large amount of overlap between the 4.5 and 8.5, if one looks at the percent change in the central tendency on the right, between the historical and the future epochs, there's notable percent increases across the board, particularly between the historical and 8.5. Now, most interesting to me is that robust increase found in those cumulative areas of strong and extreme, what we consider strong and extreme UH thresholds of 100 and 200 meters squared per second squared, which illustrates that overall populations of supercells may go up from anywhere to 5 to 6% to as much as 25%, but strong and severe events may really expand in future climates. So the ceiling for more intense supercells is much higher in warmer climates. Now, this is really fascinating. We looked at this seasonally, and yes, there will be significant increases in what we would consider late winter and early spring in the warming climate, particularly February, March, and April. So we have an early onset of the severe weather season effectively. And overall, the populations in May don't change that much across the epochs, but there are actually overall declines in June and July in the warming climates. You might go, well, what's going on there? Now, this is perplexing, of course, but if you look at if you know a little bit about the GCMs and what they're projecting in terms of moisture and instability, and of course, convective inhibition, the hypothesis of potential increase in moisture in CAPE makes sense for the spring early onset, or increase in the spring early onset. Now, conversely, projected drying and warming in the southwest and high plains in future climates should lead to a more robust elevated mix layer, which when advected over the supercell corridors should cap storm production and reduce populations. And I bet my friends out there that are in the south central Great Plains or in the western high plains or even the central plains are shaking their head probably with a nod of yes. This year was a good example of kind of representative of what we're expecting to see in the 21st century, perhaps even escalating. So to summarize the potential changes in severe storm risk in the 21st century, we will likely see an increase in frequency, but I think the big take home here is an increase in variability. We always are talking about the extremes, but to me, the real big fingerprint of climate change on almost every sort of weather variable that we measure, climate variable that we measure, and certainly perils, is variability. The variability, the standard deviation, is going to get bigger and bigger and bigger as we move in the 21st century. So in terms of severe storms, it's also likely that we'll see an earlier season start with the overall season running later. Other research by folks like Jeff Trapp, Kim Hogoin, and their research group suggests there'll be a possible increase in particularly intense storms in the warming and moistening world. Now, there is a little bit of a caveat in that a lot of our simulations have looked at the 8.5, which is kind of that extreme pessimistic warming. In fact, we're one of the few groups that have actually looked at middle of the road warming with our 4.5. So that's, we're trying to give you kind of a perspective on what the future climate might reveal. But when we're talking about, let's circle back to disasters, and we look at the framing of their cause around climate change. In many cases, we're missing this kind of elephant in the room. And as I've already argued, disasters are social constructs. They are not natural, but rather a product of society, and are caused by extreme events interacting with societal vulnerabilities through multifaceted human decision-making processes. So when we talk about changing landscape of severe thunderstorm disasters or what other type of hazard-related disasters, we must consider developed landscapes, humans, and their vulnerabilities. And I'm going to provide you, obviously, here with this kind of coastal example of the physical vulnerability that we've put into place. Now, looking at the housing unit density across the United States, both historically and into the future, this is some of the work I've done with Stephen Strader. We note that exposure has amplified rapidly and is arguably one of the primary drivers of what we're seeing, right, in changing frequency and consequences. Specific to the U.S., the population has more than doubled in the past 80 years. Housing units have increased well over 300% since 1950. Urban footprint has increased by 5x. And the developed land represented only about 2.5% of the total land area in 1940. And projections are for the end of the 21st century that developed land will take up as much as 18% of the CONUS. It is this developed character that I and my colleagues, particularly Stephen Strader, have spent a lot of time studying, trying to understand how physical vulnerability of exposure, this characteristic, is influencing disaster frequency and magnitude. And we've kind of come up with this concept of the expanding bullseye effect. That is that us, these targets, humans and our possessions, are increasing as populations grow and spread, which is leading to an escalated exposure of population-built environment to hazards. And I show you an example of a tornado scenario through Wichita here. So let's look at a couple of recent examples. There's a great paper, an article in the New York Times a few years back looking at the changes over the last decade. And what you're seeing here, red, is literally new development last decade, which is just remarkable to do. I wish we could do the same with China, and it would be even more remarkable. So here's a couple of examples of the change that we've seen in some of our locales down in Houston, which we know is flooding capital of the United States now. How about down into Central Florida, Phoenix, of course, the Bay Area, which this is not only a hazard. We think about the San Andreas Fault, we're probably going right through this neighborhood, but also, water resources and sustainability of the local economies there. So using my favorite website on the internet, Google Time-Lapse, we can see the dramatic changes in our backyard. This is on the southwest side of Omaha. In fact, it stops in 2016. You can go to the website and look at the more recent additions that they've had. This kind of sprawling nature puts more and more people at threat, in this case, to tornadoes. Now, even the most remarkable change in the world is not in the United States, it's in China. And I invite you to go to that website and kind of poke around eastern parts of China and look at the massive development we've seen in the last 2 to 3 decades. It is really remarkable to see these megalopolises just grow out of agricultural land. Really a remarkable thing that we're seeing in eastern China. And it's just not a tornado problem, it's an every hazard problem. Here you can see the dramatic clustering and growth of population density for our coastal counties. People love water, and unfortunately when they love water, they're going to sometimes be in the water. And we're seeing this, of course, with increasing sea level rise, with our extratropical and tropical cyclones, and even just full moons these days. So here's a case of just a zoomed in case of Myrtle Beach and the significant growth they've seen through last decade. So about a decade ago, we started what we called scenario-based research with the basic question of how many people and houses would be affected by a tornado over time. I'm giving you 3 examples here of Moore, 2013, Plainfield in my backyard here in the Chicago area, and Tuscaloosa, kind of 3 infamous tornado events. And you can look at the changes here between 1950 and 2010 and the percent change on the far right. And these are really astronomical numbers. And you can see that when these tornado events occurred historically, right, 1950 versus, say, 2010, they're dramatic changes in the impacts. And ultimately, this results in fatalities and injuries at the end of the day as well. So while this was great, I enjoyed this sort of singular expose into individual events. I really wanted to build something bigger. And I did so with my colleague, Stephen Strader, and as well as Tom Pingle, who's now at Virginia Tech. And I'm just going to show you this by looking at a single tornado here. We call this the Rochelle-Fairdale tornado of April 9th, 2015. A very beautiful tornado, but unfortunately a deadly tornado that struck just about 10 to 15 miles west of my location right here. So what we came up with is this sort of Monte Carlo modeling where we can take a single tornado or we can take multiple attributes across a climatological 60-year period that we have with storm data and generate these synthetic tornadoes across whatever sort of cost surface. In this case, we're looking at housing units. And we can simulate this and start to create these probability of exceedance curves. So here in this case, you see 1950, 2010, and 2070. We can put these into these probability of exceedance curves. By simulating these events 10,000 times, you get these nice smooth curves. And ultimately what you can see is that the stretching of that impact magnitude curve, that particularly the orange and then the red, stretching that out along the right side there, means that we have greater probabilities as we move into the future, currently and in moving into the future of, unfortunately, these sort of mega disasters. For instance, a 4,000 housing unit impact would be on par with a Moore 2013 tornado disaster, and a 7,000 housing unit impact would be on par with a Joplin 2011 tornado disaster. So it's not unheard of, and we have pretty good probabilities now of seeing a 10,000 or as high as a 20,000 housing unit impact tornado event. That's really hard for us to fathom, but it is certainly within the realm of possibility. So my colleagues, again, Stephen and Tom Pingle, Stephen Strader and Tom Pingle did a marvelous job of building this Monte Carlo, and we can now we can look at changing climate, and then we can actually look at the changing human landscape as well, and commingle those in sort of an experiment. Much in the same way that we do with you might remember the ideal gas law, where we hold one thing constant and see how the other variables change. And that's what we're doing here. So in this expose that we did in climatic change in 2017, we actually looked at the east central part of the United States, which has more tornadoes than pretty much anywhere in the world. And we modified, or had a baseline of 2010, but then we modified the exposure to 2100. So change the housing units, which you can see on the top right here, the 2100 scenario. And then we actually held the housing units constant to 2010 and changed the risk. And now in changing the risk, we actually increased the tornado probability and variability by 50%, just to see what would happen, right? And this is actually pretty on par with some of the research that's suggesting that tornado events might become more frequent in the 21st century. And then, of course, we allowed risk and exposure to change, ultimately to see what realistically might happen in the 21st century, because unfortunately, we're not going to hold climate the same and we're not going to hold exposure the same. So in reality, we're going to see both of those variables changing. And this is the result. The product we get is this probability of exceedance with annual housing units impacted along the bottom and the probability of those thresholds being exceeded along the y-axis. The dashed line is the 2010 baseline. So just imagine if this is kind of current, or at least last decade's baseline. The orange is where we changed the tornado risk and held housing unit exposure constant. And the red is where we changed housing unit exposure while holding tornado risk constant. Now, some of the results here, if we change the risk with a constant exposure, we see a tornado impact potential, we increase the tornado impact potential about 1.5. When we change exposure with a constant risk, we get a doubling of the high-end tornado impact potential. And then ultimately, if we do the more realistic case of changing risk and exposure, we see, unfortunately, a threefold increase in the annual tornado impacts and disaster potential from 2010 to 2100. The real take home, to me at least, looking at the bigger picture, is that while climate change is certainly this massive issue that we must address and is probably affecting things like tornado events, societal change contributes more to the potential increase than actual climate change-induced changes in actual tornado risk. Now, while this is an eye-opening experiment, we got to move beyond simply looking at physical exposure and understand that much of the vulnerability is driven by what we call socioeconomic issues. Now, this underlies the kind of the exposure landscape out there. Now, these variables play a huge role in resilience, achievement, and prosperity, and simply even an understanding of one's place within these sort of risks. So understanding where and why tornado disaster has been a real passion of mine for over 20 years. And this started back in, about 20 years ago when I wrote these papers on looking at this discrepancy in where tornadoes occur versus where their deaths are most frequent. And so you can see the illustrations over on the left. And I give you kind of a summation of some of the factors, and we could probably debate these and their contribution to the overall distributions that we see over the left. But the overall arching theme here is that we have an overlap of both risk and vulnerability that lead to these distributions. It's just not as simple as saying, oh, there's more tornadoes here, so there should be more tornado deaths. It doesn't work that way. Ultimately, you're seeing the effect of socioeconomic vulnerabilities teasing out within the mortality data. And it's particularly the mobile home or manufactured housing that I'm going to kind of end this talk with. But like we did with the Midwest or Northern Illinois area, we can do the same with the Mid-South. And the Mid-South has seen the most growth of anywhere in the United States, at least tornado-prone regions here. And you can see the dramatic increase in the potential for the housing unit impacts as we move from 1950 through 2100 here, increasing the probabilities, unfortunately, of disaster across this very, very vulnerable part of the United States. So a take home here is that different societal groups share similar exposure to the hazard, yet the hazard has varying consequences for these groups because they have diverging capacities and abilities to handle these shocks or stresses that a hazard might produce. We know that poverty is a leading cause of vulnerability. However, poverty is not synonymous with vulnerability. We can see poverty manifest itself often in the type of structure a person seeks as their home. And ultimately, the quality of the built environment influences our vulnerability. And we can see this play out in tornado mortality statistics. Here we can see that despite manufactured housing only encompassing about 7 to 8% of the U.S. housing stock, it is a location of tornado deaths for a near majority of victims. And in the Southeast, some counties have upwards of 60% of their housing stock in mobile homes or manufactured houses. That percentage is only growing as the industry continues to surge of growth due to affordable housing and a lackluster regulation and land use planning. Indeed, Harold Brooks is a wonderful graph by Harold and previous work by Chuck Doswell, revealing this sort of dichotomy in death rates or mortality between those in manufactured housing versus permanent homes, where we've seen a dramatic decrease in those that are living in permanent, whereas the manufactured housing is actually stabilized or is actually increasing in the last 20 to 30 years, which is an unfortunate consequence of this vulnerability I'm talking about. But geography is also important, and you can see that manufactured homes are not equally distributed across the landscape. Some great work that I've done with Stephen Strader looking at the differences in manufactured housing, basically census distribution of Alabama versus Kansas. And you can see that Alabama has a much greater impact potential when it comes to manufactured housing. And thus is one of the consequences of why we see such a mortality maximum in this particular area of the United States. In fact, the distribution of manufactured housing in Alabama is much different than in Kansas. In Kansas, you see most of your manufactured housing clustered within actual neighborhoods, what we call quote unquote parks. That is not the case in Alabama. While you do have parks, you have a wide distribution, particularly rural communities, of manufactured housing kind of dotting the landscape. So this issue is not going to be solely fixed with improved weather models or better forecasting, because what do we tell these people to do? We tell them to seek shelter, right? Well, often they don't have shelter. They don't have shelters, and only about 30% of mobile home residents actually have shelter. Actually, less than 20% of manufactured housing parks in the Southeast actually have sheltering. So as we look to the future, we can conclude that we're loading the dice. On one hand, the initial implicit and explicit research that we've talked about on the changing severe convective storm landscape suggests that we'll see a greater frequency and variability of severe convective storms. Thus, risk will increase. On the other die, we see increasing exposure, which is at least a first order look at the vulnerability problem. More exposure, more impacts. Ultimately, when we throw these dice down on the ground and roll them, we'll see that the odds of a disaster are actually increasing as we move through the 21st century. So while climate change may modify the tornado and other hazard seasonality, frequency, and magnitude, it is the overlapping risk and vulnerabilities, including most importantly exposure, that create disasters. And this is my primary thesis, that while the hazard landscape may change, the dominant dynamic leading to unnatural disasters is the same everywhere. Growth and development continue to put people and property at risk, from overdeveloped inland floodplains to fire-prone western woodlands to crowding coastlines to, of course, homes, businesses, and manufactured housing in some of our tornado alleys. And squabbles over the evolving field of attribution science, that is, parsing what portion of the storm is due to climate change, distracts from the attention from the utter clarity around the role of on-the-ground decisions or indecision in worsening damage when bad weather strikes. To summarize, what I see is what's occurred historically and looking into the future. We could say on the left here is the annual hazard frequency of floods. It could be heat waves, it could be tornadoes, it could be hail events, whatever you want to pick. What the point is that we're seeing increasing frequency, also increasing variability as we move into the future. Most importantly is that red area, which is our exposure. We're seeing increasing exposure and what we consider an unacceptable tolerance window, which results in disasters, which you can see as we move into the future. I expect more and more of these events of increasing magnitude and impact. So we have lots of tailwinds and headwinds, and we could spend really an entire month probably discussing all of these. And I just give you the fact that we do have some tailwinds, which is always a positive, but we do have a lot of things that are giving us headwinds in terms of fighting this disaster landscape. I invite you to take a look at these on your own. I'm the biggest proponent for building codes, and most importantly, starting to think about land planning, which in certain parts of this country we really don't do a great job. In my backyard, we have very significant restrictions in development, but where I grew up in Georgia, it's pretty much a free-for-all, and this patchwork leads to, unfortunately, differentiation in vulnerabilities and impacts across the landscape. At the end of the day, the real challenge, as I've determined, is not scientific. It really is a social and political issue. So if our goal is to successfully reduce hazard impacts and build societal resilience to weather and climate perils, then when we go to the AMS conference or go to the National Weather Association, we really need to see that the physical and social and even behavioral sciences are all talking in the same room. We got to learn from each other and work together to hopefully inform policymakers, not only at, say, the congressional level, at the federal level, but really at the local level. Because a lot of times land use and building codes are implemented and enforced at the local level. In fact, almost all cases across the continental United States. That's where you meet the rubber meets the road. So I hope that stirred some attention to this subject and maybe got some fire under you to look into this in a little bit more detail. But I thank Jenna and Ray for your, and all of you for your attention today, and I'll conclude there.
All right, great. Thank you so much, Walker. Can you hear me?
I can.
All right, great. Awesome talk. And I will start going through some of the questions. We got a couple of questions here. I'm going to actually copy and paste them into the chat so you can read them as well. Hopefully you'll be able to see them. But first question is, when you refer to tornado risk, are you actually describing threat? I say this since exposure and vulnerability are part of the risk equation. So if exposure increases, is vulnerability, i.e. socioeconomic and demographic vulnerability, included in the tornado risk function?
That is such a wonderful question, because I spend in my my hazards and disasters course, we spend probably about a week looking at definitional issues. As I try to allude to in a lot of my papers, because defining things is important, and even the disaster science research, we debate about how to define something like risk. Particularly the word that sees the most strife is vulnerability. But risk, when I'm talking about risk, I'm talking about climatological risk. So what is your probability of seeing think of it as the SPC, your probabilistic chance of seeing a tornado within 25 miles of one point. So while I understand your equation, oftentimes look at risk in a sort of different perspective, understand that when I'm talking about risk commingling with, say, vulnerability, I'm looking at the climatological risk, the probabilistic chance of an event occurring. A hazard occurring. And so it says if exposure increases, is vulnerability included in tornado risk function? Yeah, so usually these are two sides of, so what I look at is try to show with that experiment is we will hold exposure constant, which exposure one could debate is the most physical vulnerability factor. Right? You got to have something there that it's exposed to be considered socially vulnerable. So we got vulnerability, which is defined at least at the outset by exposure. And then over here, we have the climatological risk. And what I was doing is changing one and seeing what would happen to the other, ultimately in terms of impacts. Now, impacts are what I would consider the results, the disasters. And so we might want to say a 100 housing unit or 1,000 housing unit or a 2,000 housing unit event is considered a disaster. We could debate all day about what those thresholds might be, but if it strikes your house, I bet it would be considered a disaster. It's a wonderful question, and boy, we could debate all day.
Okay, great. Just a reminder for those, if you guys do have questions, you can type it into the chat box. The next question by the same person, did you look at the study by Strader, and I'm going to get this name wrong, Roosh et al. On survivability of better versus poorly anchored manufactured homes in Lee County, Alabama?
Yeah, I mean, Stephen is my former PhD student, so I do know Stephen all too well. And he's done some great work. And David down at Auburn is certainly one of the, let's call it up and coming stars in wind engineering. And there's just a great group of researchers at Illinois, Florida, and Auburn doing some really phenomenal work in that field. Yeah, at the end of the day, this comes back to when you talk about manufactured housing, and I'm not even going to get into talking about nomenclature, mobile versus manufactured. There's some interesting reasons why we call them that. But let's just call it broadly manufactured housing. One of the biggest things that David, and through his engineering studies, has found that is that the biggest problem, biggest factor, even in weak tornadoes, so EF0, EF1s, is the fact that many of these aren't anchored, or if they are anchored, they're anchored improperly. And I think a lot of that comes back to enforcement in local communities, right? Oftentimes the manufacturer of the manufactured housing is different than the installer, and the installer oftentimes doesn't do a great job of anchoring, if at all. And a lot of this just isn't mandated, or if it is mandated, is not checked correctly. And it's certainly not followed up upon 5 or 10 years where these things might rust out. And I think what you're seeing is a lot of the effects of socioeconomic vulnerability, whether it be in the county and their inability to hire somebody to go out there and inspect these, to the individual homeowner who just doesn't have the capability to, upgrade the anchoring system. But I think you point out a good point. That really is boots on the ground sort of understanding of vulnerability. Something as simple as an anchoring of a manufactured house or lack thereof. And what happens, by the way, when these things are not anchored correctly is the house just rolls and falls apart. And what you find is deaths in relatively weak, quote unquote, weak tornadoes, which in a permanent house would never occur.
All right, thank you. Are there any other questions? I'm not seeing any right now. I'm going to put the link to where we will post the recording in the chat box. All of our webinars are posted here after they're completed. Just give it a day or two so our webmaster can get that uploaded. Ray, did you have any parting thoughts or questions?
Sure, Jenna. I just mentioned to the Weather Service folks on the call to be sure and share the presentation with others in your office, especially your WCM. I think this is really illustrative of where we're headed as an agency by looking not only at the weather climate, but also the people side of it. And we've heard looking at the social vulnerability aspect, especially in the last year or two, now becoming part of NOAA's strategic plan and will eventually, I'm sure, show up in Weather Service. So, and I'd encourage you to check out Walker's website. There are a number of great papers. I keep poking them to put it all into a book, and maybe someday I'll have poked him to the point where he gives in and does it. But a lot of excellent knowledge that's very practical for us in the field on the people side of the equation.
Thank you, Ray. And thank you, Jenna.
All right, well, thank you guys. I don't see any other questions. So great talk again. Thank you, Walker, so much. Thank you, Ray, for setting this up. And we will be in touch with our future webinars. We don't have anything on the schedule right now, but hopefully we'll be having something for late August, September. Oh, wait, one other last question just came up. As a follow-up on the risk terminology, here is how FEMA defines risk equation, where probability is described as a threat rating. Oh, and there was a link given, so I'll put that in the chat as well so that you can have it.
And I'll argue that the IPCC, it comes up, there's some great papers out there that literally do nothing but do a census of all the different ways to define things like risk, like vulnerability. So it's a very complex, you'd think that we'd have it figured out how, it seems like a simple term, but boy, when you get to the nuts and bolts of it, it gets quite complex. So I invite you to take a look at the varying definitions. And like I said, at the beginning of my papers, I always try to describe what I'm looking at to make sure that the reader knows. And maybe I should have done a better job during this talk of explaining exactly what I was looking at.
All right, well, thank you so much, Walker. And thank you, Ray, again for setting this up. And we will have the talk posted in another day or two, and we'll send out an announcement when that happens. All right, thank you, guys. Have a great day.